two picture changing operators, and then you have to add hello.
Yeah. Can you repeat again?
Yeah. Last time you had these two picture changing operators, and in the end you have to add this contribution coming from this non-trivial area.
Exactly. Yeah.
Like if I just consider this moduli space and construct all these chambers and this vertical
Yes.
bars connecting them and so on, if I just do the integral, like it is already there, right? It will automatically be there if I do the integral
Yeah.
using all the
Meaning
moduli.
you have to choose a section, right?
Yeah, so I have sections and then I have this T1 and T2, which are these horizontal coordinates. So
Yes.
if there is no holes, then I do the integral, then this
Yeah.
area will be automatically taken care of, right?
Exactly. Yeah.
Okay,
Yeah.
okay, fine.
Integrating over the area basically fills the gap in the whatever gap you are left with,
Yeah,
right? It fills that gap.
okay, okay, fine.
Okay. Any other question? Okay, so let me then start. So what we have discussed so far, okay, is the procedure for doing the calculation for generic choice of momentum. Okay, so for generic choice of momentum, we have discussed what the procedure is. Now, as I said, for spatial momentum, and also when some internal momenta are forced to be spatial, we need to use string field theory. And this I describe some example. For example, in quantum field theory, for example, if you have a diagram like this in QFT, this momentum is spatial because if this is k, this is also forced to be k, and you have k square plus m square equal to 0. So this gives you vanishing propagator or a divergent propagator. So 1 over k square plus m square, okay, that comes from this line, this is infinite. And this basically says that we cannot do naive sum over Feynman diagrams. We need LSC. And the point is that the standard worldsheet calculations, they basically do naive sum over Feynman diagrams. So if we have a worldsheet like this, so that divergence, for example, will come in the following way. That imagine that you have there's a one loop diagram. So imagine there is one vertex operator here and three vertex operators here. So when this degenerates, we get integral dq over q, q to the power k square plus m square. Okay, terms like this. Okay. And this, because this is 0, this is forced to be 0, okay, we get integrals. So this is from integral 0 to 1. This is infinite. Okay, that's basically the same physics, because you are writing 1 over k square plus m square in this form when you are doing worldsheet calculation. Okay. And then similar contributions from tadpole diagrams, for example, where again the momentum is forced to be 0. Okay. So this is also divergent. Let me draw this a diagram like this. This is there is a torus over here. So the loop is here, right? Imagine that there is a torus over here, and then so we have a 4-point function. Okay. This, in the language of string field theory, or in the in the language of string field theory, will come from diagrams like this. Okay, or there may be other Feynman propagators in this part. Okay, but the main point is that this momentum, this is k equal to 0. Okay, and if there is a massless field propagating here, you again get 1 over k square, which is infinite. Is this okay? Are there questions? So I'm not going to describe the full string field theory method because that requires introducing string field theory. Okay. But I'll specify some consistency requirements that one has to satisfy. Okay, so SFT can handle this. But in order to be consistent, with SFT, the worldsheet procedure has to satisfy certain consistency conditions, and that's what I'm going to discuss. And these consistency conditions again can be understood in terms of Feynman diagrams. So imagine that suppose in QFT you have a Feynman diagram. Then imagine that you have a Feynman diagram like this, which has a single propagator connecting two blobs. Okay. Inside this, there may be arbitrary Feynman diagrams, which you don't care at this stage. Okay. These itself may involve loops, etc. But let's just focus on this propagator. Suppose we are in the regime where this propagator is going on shell. Then the particular property that this Feynman diagram has is that this should go as 1 over k square plus m square. Okay, that's the propagator. Okay. This may have numerator factors which will have to come appropriately. But whatever is a propagator, this propagator will appear here. Okay. And then it will be the product of two amplitudes, A1 and A2, okay, where A1 refers to this amplitude and A2 refers to this amplitude. Okay. And this property is satisfied irrespective of whether the external lines are on shell or off shell. This is true for any off shell external lines. Okay, that the fact that the contribution from near the pole will just become product of this amplitude and this amplitude multiplied by the propagator. So the idea is that if the worldsheet expressions that you have given has to be treated by string field theory, it better be that the worldsheet procedure is consistent with this factorization. Because otherwise, the worldsheet diagrams will not have interpretation as string field theory diagrams. And what we are going to study is what it implies for the worldsheet prescription that you have given so far. Is this clear?
So this factorization always happens, no? In momentum space, why not?
Yes.
A1 times A2 times.
Yeah, in Feynman diagram, it happens. Right?
Like you don't need this on going on shell, right? Even generally, this is the
Yeah, true. It generally
okay.
also it can happen, exactly. Right?
Okay.
But if you are just looking at the residues at the poles, right, then it can be distinguished from the rest of the contribution. Because this kind of divergence will come only from Feynman diagrams of this kind.
Yeah, true. Yeah.
Right? So this allows you to isolate this from the rest of the
Yeah.
contribution.
Yeah.
So what?
Could you repeat what you mean by the worldsheet should also have this? Because in the way you have written worldsheet amplitude, we've
Yes.
already integrated over the modular space, right? And we don't have individual diagrams.
But we can divide, as I said, that the same integral I can write as a sum of many terms, right? And each term can be thought of as a Feynman diagram contribution. That's
So
what
in
happens.
so in doing that, you should see this factorization happening in each of these diagrams in some sense.
Exactly.
I see.
Right. So what I'm going to discuss is what it implies for the worldsheet amplitude. So what does this imply? So in the worldsheet, then we are considering a degeneration of this kind. Okay, that Feynman diagram contribution is representing a degeneration of this kind, where this corresponding Q is going from 0 to 1. Because that's the way you represent the propagator in the worldsheet. And here there may be holes, vortex operators, and similarly here. So the idea is that the full contribution near Q equal to 0 should behave as if it's the product of this amplitude and this amplitude. Now this of course is a property of CFT. Okay, that the CFT correlator factors into the product like this. Right? That's the reason why we can interpret these diagrams in terms of string field theory diagrams. Okay, this we have already discussed, that we insert this phi r on sigma 1, phi s on sigma 2, right? If we call this sigma 1 and sigma 2, and then we use this propagator, which is phi rc b0 bar L0 plus L0 bar inverse delta L0 bar phi sc. This L0 plus L0 bar inverse basically comes from the integral, right? Integral dq 0 to 1 to the minus or q to the L0 plus L0 bar. So the worldsheet already achieves this factorization. But we have to make sure that whatever extra data that we are providing should also be consistent with this factorization. And the extra data in this case corresponds to the location of the picture changing operators. Okay? That's certainly an extra data because that worldsheet doesn't tell you by itself how you should choose the location of the picture changing operator. That is something that we specify, right? Because that's the choice of the section. The other information that is not important, not necessary for on-shell amplitudes, okay? But when you are trying to define off-shell amplitudes, okay, it makes a difference, and that is that if you recall, around each of these punctures, we cut out a disk and introduce a local coordinate system, WA. So the idea is that the constraint that you have to impose, okay, is that when you start from this big Riemann surface, which contains sigma 1 and sigma 2, and when you go near the degeneration, okay, then the choice of local coordinates that you have made on this big Riemann surface, okay, should agree with the choice of local coordinates that you have made on the smaller Riemann surfaces, that is different moduli space altogether, right? And at the same time, the choice of PCO locations that you have made on the big Riemann surface should agree with the choice of PCO locations on this as well as on this.
Ashok, hello.
Yes.
Yeah, I have a question actually. This this diagram, when you insert this phi r, phi s, and so on,
Yes.
this already looks like this factored form, right? Like the QFT amplitude, with this k square plus m square being this matrix element kind of.
True.
Yeah.
True.
Then what is the next statement?
Yeah. The point is that the PCO assignments here and here,
Uh,
okay, and the choice of local coordinates here and here,
yeah.
they are induced from the full surface sigma, right?
Yeah. True.
Okay. So that surface is completely different Riemann surface as compared to sigma 1 and sigma 2.
Yeah.
Okay. So while defining amplitudes on sigma, we would have defined, we would have chosen some PCO locations, right?
Yeah.
Do you mean union or intersection?
No, it called sigma contains both, right? Sigma is a big Riemann surface. Before before you have reached the q equal to 0 point, it's just a single Riemann surface, right?
Yeah, so it's union, right? It's a
Sorry, union. Yeah. Okay. Yeah, not intersection. Thank you. So the point is that on sigma, we had chosen already some PCO locations. Okay, that is a priori independent of what you have done in the lower Riemann surfaces. But near the degeneration, you have to make sure that the PCO locations that you have chosen on sigma are consistent with the PCO locations that you have chosen earlier on sigma 1 and sigma 2. Similarly, the local coordinate system that you have chosen on sigma should again be consistent with the local coordinate system that you have chosen on sigma 1 and sigma 2.
you briefly mentioned that this is for some off-shell things. For on-shell, it does not matter.
Yeah, for on shell, the W's don't matter, right? Because if you change local coordinate, if this is a dimension, okay, it matters if you have chosen a representative of off shell amplitude, which is not dimension 0 primary. Okay, there it could matter.
Why is this happening? Could you illuminate?
Why is this happening?
Yeah.
Yeah, see, the change of the local coordinates or the change of PCO locations is a boundary term, right?
Okay.
Okay, it's a total derivative. And total derivatives integrate to 0 in most cases. But when there are the spatial momenta, okay, then they don't integrate to 0, right?
How
Because
do you
then,
see this? Sorry, I'm not able to visualize what you're saying.
yeah. So what I'm saying is that let's think of whether the choice of PCO location, let's forget about the local coordinates, okay? Let's look at the choice of PCO locations.
Okay.
If you move a PCO location, that's like changing the section, right?
Yes.
Okay. And as you saw, difference between the two sections is the integral of a
Boundary.
total derivative.
Yeah.
Okay. So that integral over the total derivative can possibly a big contribution from the boundaries or the moduli space, right?
Yeah.
Okay. But we had argued that if the boundary, let me go to the next.
Boundaries are the degenerations.
Yeah, boundaries are the degenerations.
I see.
Okay. That if the boundary, if the momentum that is flowing at the boundary is generic, then by analytic continuation, the boundary terms all vanish.
I see.
But if the momentum is not generic, right, which is what will happen, for example, here, if there is only either 1 or 0 points on this side, right, then this momentum will either be forced to be 0 or on shell.
Yeah.
And then we could possibly pick a boundary contribution from here.
Okay. Can we quantify this, what you are saying?
Can we quantify this?
Like the explicit expression of the boundary term?
Well, explicit expression depends on the details of the of the
Riemann
that what amplitudes you are considering, right? So
Yeah.
basically, what that said, that the argument that we had given is that integral SGMN minus integral over S prime GMN, and you are integrating over omega GN 6GG, in this case GMN 6G minus 6 plus M plus N, right? This difference you had argued is given by the integral of a total integral of d omega GMN 6G minus 6 plus M plus N, and this integral is over a surface R GMN, okay, which binds S and S prime. Is that clear? Because this is S is S prime and this is R. This
Yeah,
region.
this statement was also only true for on-shell things, right? When the external things are on-shell.
No, this you can generalize to off-shell if in this choice of section you also include the choice of local coordinates, then this becomes an off-shell statement also. Okay? But let's not worry about this for now. Okay, let's suppose you have on-shell amplitudes, but PCO locations have changed.
Okay.
Okay, then this is true, something like this. And this will integrate to 0 if the boundary terms all vanish.
Yeah.
Okay, so this is 0 if we can ignore boundary terms. But at q equal to 0, or if it nearly equal to 0, if the momentum flowing through has k square plus m square equal to 0, then we cannot ignore boundary terms. Right?
Yeah.
So the idea is that in this case, that's the situation you are considering. Okay? If the momentum flowing along this is different from is not on shell, right? If it's generic, then there is a problem. Okay? But if the momentum that is flows through this is spatial, right, which makes k square plus m square equal to 0, then the boundary terms are important, and you have to make sure the boundary terms. So then the boundary terms were given non-vanishing answer, right? Is that clear?
Yes. Yeah.
So we have to make sure that near this degeneration, okay, the boundary, the sections that you have chosen, okay, should be fixed and they shouldn't have a freedom. Because if you try to change the section, okay, by moving the PCOs, okay, then we may get a different answer because we may pick up some boundary term from here.
Yeah. And in the next page, whatever you were writing, this S minus S prime, the
Yes.
way we argued that this is 0 is because d omega itself is 0 in the bulk when all the states are on shell.
That's true. Yeah. So this is omega, but this is true if if this is S and this is S prime, right? Near the boundary, we have to ignore this contribution, right?
Yeah, I agree.
Okay. So that is what we are discussing here.
Yeah, so ignoring that and demanding on shell gives you choice of independence of the section.
Exactly.
But I still wanted to ask this off shell thing. You were saying something.
Yeah. So what I'm saying, okay, off shell will come to. So the idea is that the S and S prime should agree near the degeneration, right? Maybe I can put it that way.
Okay.
So these are the q equal to 0 points. Okay. then these boundary contributions, that is some other q prime equal to 0. Then these boundary contributions don't have to be dealt with, and with this argument applies.
Yeah.
Okay. So first let's finish the PCO, then we'll come to the off-shell thing. Okay. So let's suppose that you have on-shell external operators, there are dimension 0 primaries. Nevertheless, we can see that so what this is saying is that it better be that somehow near the degeneration, the PCO locations agree. Okay, that you shouldn't be able to move the PCO independently near the degeneration, because then again the choice of section independence comes in. Okay. So the question is, what principle fixes the PCO locations near the degeneration? Okay. And there we draw insight from these Feynman diagrams that the way we should choose the PCO locations near degeneration is that they must agree with whatever you had chosen on sigma 1 and whatever you have chosen on sigma 2 in earlier analysis. Okay. So let me write it again. We have this picture over here. This is sigma 1, this is sigma 2, and then you have various. So these are either sigma 1 and sigma 2. So sigma is the total. So sigma 1, sigma 2 are lower genus or lower number of vertices or both. So while analyzing the contribution, while defining the amplitudes on sigma 1 and sigma 2, we would have already chosen some PCO locations, right? Because for this, you would have chosen how to choose the PCO locations at various points in the moduli space. On this, you would have chosen how to choose the PCO locations at various points in the moduli space. Now, sigma is a different Riemann surface. So a priori, it has completely independent choice of PCO locations. But the constraint that you have to place on sigma, on these choices, is that near degeneration, PCOs on sigma should agree with the PCOs on sigma 1 and sigma 2. Is this clear? Because once you demand this, then there is no choice. The boundary, or if you choose two different sections on sigma, right, say S and S prime, near degeneration they get pinned, because they have to both satisfy this condition that their PCO locations must agree with the lower genus Riemann surface PCO locations or lower number of punctual Riemann surface PCO locations. Okay. So this is what pins the S and S prime near the boundaries. Is this clear? Are there questions?
Isn't it, I mean, too constraining, it seems, or maybe it works because, like, for like each degeneration you reach one particular boundary.
Exactly. Yeah.
Okay.
Right. And the point is, in the middle you are allowed to do vertical jumps, right?
Okay. Oh, in the middle we are allowed. Okay.
Yeah.
Right.
In the middle you are allowed to do vertical jumps.
Okay.
So this is the constraint you will impose on the choice of PCOs.
Ashok,
Yes.
like this S and S prime should agree near Q going to 0.
Yes.
Why? That is true, but why does it have to generic momentum? Why is there no issue?
Oh, in generic momentum, what happens is that if you have integral 0 to 1 dq q to the alpha minus 1, then this is 1 over alpha, right?
Yeah.
Okay. At generic momentum, so alpha, if alpha is generic, then we take this to be the definition. Even for alpha less than 0. Okay, for alpha less than 0, this is divergent, but nevertheless, we just take this to be the definition.
Yeah.
Okay, and we had discussed that if we use this procedure, then total derivatives always have no boundary contribution from 0. Okay. So suppose you do this integral 0 to 1 del q of q to the beta minus 1, say, or q to the beta. Beta is an arbitrary number, right? So let's do this calculation in two different ways. Okay. One is that I can do this integration by parts. Okay. And I write this as q to the beta at 0 and 1. Okay. The other is that we just differentiate and then use this rule. Okay. So this is as integrate as total derivative. Otherwise, you do this integral 0 to 1 del q of q to the beta is beta q to the beta minus 1 integral 0 to 1 dq. And now you use this rule over here to write this as beta times 1 over beta, which is 1. Okay. So you see this 1 is reproduced. If you think of this, the q to the beta, you pick out the boundary contribution at 1, but you ignore the boundary contribution at 0, irrespective of whether beta is positive or negative.
Yeah. Okay.
So at generic momentum, if you use this rule, right, and this is what you get from string field theory in any case, because in string field theory, this is more fundamental than this side, right? This is the worldsheet expression, but in string field theory, this is basically 1 over L0 plus L0 bar. Right?
Yeah.
And that's the starting point. Then you use the Swinger parameterization to get to this form.
Yeah.
Okay. So from string field theory perspective, this is the correct procedure, and that allows us to ignore the total derivatives.
Okay. Okay.
Except when alpha is 0, right? Because then
Alpha is 0. Yeah.
doesn't work. And you have to do special thing with string field theory.
Yeah.
That's
Okay.
this particular procedure only for only when the momenta is special. Okay, is this clear?
Yeah. Yeah. Yeah.
Okay, now just I don't want to go into this in too much detail, but just to answer Kaustubh's question, right, that for off-shell states, the choice of WS matter. And here by off-shell, I mean any state that is not dimension 0, 0 primary. Okay. So something like for QB lambda, right, which is manifestly on shell, but of course it is a trivial state. Okay. But to show that it's a trivial state, we have to first know how to define its amplitude. Okay. And to define its amplitude, you need to pick these local coordinates, because if you recall, on a Riemann surface, if there is a puncture, right, the way we have to insert it, that we define this local coordinate WA and insert the vertex operator in this coordinate system. Okay. In a defined coordinate system, the vertex operator will be defined because you have to conformally transform from WA to say W prime A. Okay. So the off-shell amplitudes do depend on the choice of the local coordinates. Okay. And the one way to encode that dependence, okay, is by saying that you recall that we had defined this PGMN. PGMN. Okay, where the base was the moduli, okay, fiber was the choice of the PCOs, okay, but here I should also add the choice of WA punctures. So now the fiber becomes infinite dimensional, okay, because WA, choice of WA means it's a function, right? For every puncture you have to specify a function. Okay. Nevertheless, once you think of it this way, okay, then different choices of WA, okay, again can be thought of as changing from S to S prime. Okay. And the kind of argument that you have given for showing the independence of the PCO locations also work in the case of WA. Okay, again by using the general identity that we had described before. Okay, so that's the reason why, just like the PCO locations have to be taken to be the same on two sides, the local coordinates of the punctures also have to be taken to be the same on both sides.
But in this setup, why will d omega be 0 in the bulk? In this,
While d omega be 0 in the bulk? Oh,
yeah,
because d omega, this relation still holds. Now, the relation that I wrote down earlier, right?
yeah,
That if we call d omega was a sum of omega with q a1 plus omega a1 up to qan, right? This is the equation you used.
yeah.
So this equation holds in PGMN. This new PGMN, okay, which also includes change of local coordinates.
Yeah, this is fine, but if AIs are not BRST closed, how will?
No, then of course it's not true. But suppose AI is QI lambda.
Oh, they are BRST exact, you're saying.
Yeah. Suppose they are BRST exact, but nevertheless not dimension 1 on primary, dimension 0 primary.
I see.
Right? You can take any lambda, apply Q, right? You can take any lambda, apply Q, and that gives a BRST invariant object, right?
Yeah, yeah,
And suppose you want to show that this vanishes, right? Then again, these total derivatives will come in.
yeah, I see.
So if you have decided that you will work by choosing the external vertex operators to be dimension 0 primaries, which you can do at generic momentum as we discussed, you can take them to be CC bar times the dimension 1 on vertex operator for bosonic case, and there is a similar choice for the superstrings. Okay. Then the result is insensitive to the choice of local coordinates, and you don't worry about this. Okay. But then you cannot ask the question that what happens if you change the representative. Right? Because if you change the representative, the new representative may not be a dimension 0 primary. And then we cannot even define its the amplitude for these unless you have made a choice of local coordinates. Is this clear? Okay, so now we come back to PCO. So we have this picture. This is sigma 1, this is sigma 2. Okay. So let's suppose that on sigma 1, we have M1 NS and N1 R. And let's suppose that on sigma 2, we have M2 NS and N2 R. Okay, I'm not now doing just one side, right? Let's say heterotic. Okay, so that you don't have to talk about NS, NS, or RR, but it's very similar. Okay. And further, let's suppose that the state that is flowing through this, okay, is Ns. So let's just do some counting to see if the procedure that we have specified can be implemented or not. So if this is Ns, then effectively sigma 1 has one extra Ns node, right? So instead of having M1, you'll have M1 plus 1 Ns. So the number of PCOs on sigma 1, okay, imagine that we didn't know anything about the sigma, we only knew about the sigma 1s, and we had chosen some PCO locations appropriately on sigma 1. Then the number of such PCOs will be given by 2G1, oh, I should say also genus 1, genus G1, and this is genus G2. The number of PCOs on sigma 1 will be 2G1 minus 2 plus M1 plus 1 plus N1 by 2. And number of PCOs on sigma 2 is 2G2 minus 2 plus M2 plus 1 plus N2 by 2. Is this clear? But let's compare this with the number of PCOs on sigma 1 on sigma. So this will be given by a similar formula, okay, except that the genus is G1 plus G2. On sigma, the number of Ns punctures is M1 plus N1. So 2G1 plus G2 minus 2 plus M1 plus M2, sorry, M1 plus M2, and then number of Raman punctures is N1 plus N2 by 2. Is this clear? And now you can ask, do these agree? Right? Because if they don't agree, then the way we specified the way we said that you should choose the PCOs will not make sense. But we can easily verify that they do indeed agree, right? Because this here you have minus 4, but there's a plus 1. Okay? So this plus 2 will cancel, make minus 4 into minus 2, and that will agree with this minus 2. The rest, of course, agree. Is this clear? Okay. So what you are checking here is that the sum of these two should be equal to this. Okay, and you can check that they are the same. So it makes sense to say that we'll choose the PCO locations on sigma so that they distribute on sigma 1 and sigma 2 exactly the way they were if we had not known about sigma at all, but we had only chosen the PCO locations on sigma 1 and sigma 2. So now we turn to again the same diagram but with Raman puncture. Now suppose this is Raman. And again, suppose the sigma 1 has genus G1, M1 NS, N1 R puncture. And sigma 2 has genus G1, sorry, genus G2, M2 NS, and N2 R puncture. Then sigma, okay, on the other hand, So number of PCOs on sigma 1. Okay. So now you see that the number of PCOs here will be determined by not just these numbers, but also one extra Raman puncture, because this is Raman. Okay. So there will be N1 plus 1 Raman punctures on this side. So number of PCOs on sigma 1 will be 2G1 minus 2 plus M1 plus N1 plus 1 by 2. And similarly, number of PCOs on sigma 2 is 2G2 minus 2 plus M2 is N2 plus 1 over 2. Okay. Let's write down the number of PCOs on sigma. Which is the same, which is 2 G1 plus G2 minus 2 plus M1 plus M2 plus N1 plus N2 by 2. Is this clear? But now you see that there is a problem, because total number of PCOs on sigma 1 and sigma 2, I think something is wrong. Total number of PCOs on sigma 1 plus sigma 1 and sigma 2 doesn't match the number of PCOs that you need here. Is this clear? Right? Because you see here the total number is minus 4 plus half, so minus 3. Okay. Here it's minus 2. So this sum now is not the same as this sum. So this has one less PCO. Is this clear? Okay. So you see that if we had naively just followed the procedure that we described, right, which is consistent with Feynman diagrams, okay, there will be a problem, because the number of PCOs that we require on sigma 1 and sigma 2 together is one less than the number of PCOs that are there on sigma. Okay. So one extra PCO on sigma has to be placed somewhere. Okay. We cannot place it on sigma 1 or sigma 2. Okay. So the only solution is that we have to place it here. Extra PCO has to be placed here. Okay, I'll make it more manifest in the next slide. Is this clear? Are there questions?
I mean, you are saying that it should be between this phi r, phi s.
Yeah, well, I'm saying it because you cannot put it here, nor you can you put it here, right? Because that will be inconsistent with the procedure that you have described earlier.
Okay.
Okay. The only place where you can put is here. Okay, but we'll also see that there's an independent reasoning as to why there should be a PCO there. So let's recall the way we had done this factorization analysis. So the way we had described, suppose this is sigma 1, this is sigma 2. Okay. The way we had analyzed this contribution is that we think of this as dq, which is dq bar, dq over q, dq bar over q bar. Okay. And then we insert this object phi rc q to the L0, q bar to the L0 bar, B0 bar, phi sc. This is This is a worldsheet procedure. In string field theory, you would have just gotten 1 over L0 plus L0 bar times the level matching delta function. Okay, but formally they are the same. And then we had said that on sigma 1, we have a phi r, and on sigma 2, we have a phi s. And for phi r and phi s, we have chosen the standard choice of PCO of picture number, okay, which, as we described, is minus half. Okay. So phi r phi s have been taken to have minus half picture number. Okay, because that's the standard picture number. But if that is the case, then you see that you have this relation, right? Phi r C phi s is delta rs. So if this has minus half picture, then this should have minus 3 half picture. Right? Because the total picture number has to be minus 2. This is a disk amplitude. And on the disk, we know the total picture number has to add to minus 2. So if this is minus half, this is minus 3 half. So you see here you have a minus 3 half here. Similarly, here you have a minus 3 half. And this will vanish unless there is a PCO inserted in the middle, right? Because this has total picture number minus 3, okay, which is inconsistent with the fact that it has, in order to get a non-zero answer, it has to have picture number minus 2. So we need a PCO here. So this is just another manifestation of the same analysis that we did last time, that we did in the previous slide, right? That the total picture number here is calculated assuming that this vertex operator is in minus half. Similarly, total picture number here has been calculated assuming that this vertex operator is minus half picture. Okay? But this means that the phi RCs have picture number, phi RC and phi SC have picture number minus 3 half, and clearly we need a PCO to get a non-zero answer.
Oh, why did you say phi RC has to be minus 3 by 2? This is not some sphere thing, right? That the things have to add up to 2, minus 2.
This inner product is defined on the sphere, right?
On the plane safety, you're saying.
On the plane, exactly.
Oh,
right?
okay.
Because this inner product is the BPZ inner product, right? This
Yeah, okay. And even in this L0, Q bar L0 is that one.
Exactly. Yeah. All inner product is defined once and for all on the plane, right? So that is this on the plane. Okay. So you know that we have to put a PCO here, okay? But then we have to ask where, because even though it looks like a point, right? When you think in terms of this, right, it is really a cylinder that we have. Let me draw it as a cylinder. Okay. So the picture that you should have is that you have a cylinder. We have, this is a cylinder. So you have phi RC on one side, phi SC on the other side. Okay. And here you have these B0 bar insertions. This is B0, and then similarly B0 bar. Okay. And then also this Q to the L0, Q to the L0 bar. All of these are inserted by the way you define L0 and L0 bar, and again by doing an appropriate integral of t on these circles, constant time circles. And it doesn't matter if you move them around, because by conservation law, it doesn't matter. The contour choice doesn't matter, right? But it's along these contours. So here the question is, where will you insert chi? Okay, you can insert chi here or between B0 and B0 bar. Okay, where to insert PCO? Here or there. Okay, or it could be between the two contours, right? B0 and B0 bar contours. L0 actually doesn't matter because these are dimension 0. Chi is a dimension 0 primary, right? So it commutes with L0 and L0 bar, but it doesn't commute with B0 and B0 bar. And it turns out that there is a unique choice. By demanding that the insertion commutes with B0 minus. Well, you see, we have been demanding that the states are annotated by B0 minus. So if the states are annotated by B0 minus, then whatever choice of PCO location you make should be such that applying that on a state which already is annotated by B0 minus gives you back a state which is annotated by B0 minus. And this fixes the location of the PCO. This fixes the PCO insertion to be in the W coordinate. If this is the W coordinate on the cylinder, dW chi of W, or which also I can write as integral is from W equal to 0 to 2 pi, or from 0 to 1 dz by z pi of z. Okay, chi is the dimension 0 primary, so from W to Z it makes no difference, but dW becomes dz over z. So what this is saying is that, and here this fact that you don't have to choose sections, but we can make use of cycles comes into play. Okay. So what this should be interpreted as is the following: okay, that if we take this cylinder, let's not worry about the rest. Suppose you have a cylinder like this. Okay. We have been thinking that a PCO should be inserted somewhere. Okay. But as we had seen that it doesn't have to be inserted at one point, right? You could have taken this to be half chi of W1 plus chi of W2. Okay. This will correspond to choosing S to be a cycle where is the average of these two cycles. Okay, one where you place chi at W1, the other one where you place chi at W2. Okay. This is a somewhat extreme version of that, where it is saying that you take the average. Okay. I should put a 1 over 2 pi here. Okay. Where it's saying that you have to take the average over inserting it on everywhere on the cylinder. Okay, everywhere along a particular time cycle on the cylinder. Okay. And that's what this means. Okay. So this is not a section, right, but a chain or a cycle, and this particular chain has basically infinite number of sections, right, because you are averaging over continuous insertions of chi.
Sorry, I'm slightly confused. W was this is an equal tau circle or equal sigma circle?
Equal sigma circle. So, yeah, I don't remember how I defined W, but whatever is the equal sigma circle.
You're not integrating over sigma direction.
Yeah, sorry, equal tau circle. Yeah,
yeah, equal tau. But doesn't that correspond to mod Z being same rather than?
Sorry, this is yeah, you're right. This is not 0 to 1.
This is some contour around origin.
Yeah, exactly. Yeah. Yeah, this is a contour. Mod Z equal to 1.
And could you, sorry, remind me the dimension of chi, the primary?
Chi is 0, dimension 0.
It's a dimension 0, yeah. Okay.
Yeah. Okay, that's why converting from W to Z, you don't have to put any factor. It's a dimension zero operator. Okay, but you are averaging over the whole circle. And again, probably that's the 2 pi I here. Right? Because if you didn't have the chi, then this should give you 1, right? Because you are really averaging over all the insertions. Is this clear? So let me call this some G. Okay, so G by definition is G by definition is integral dz over z pi of z. So either 1 over 2 pi I is included in the definition of this contour integral. So what this is saying is that if you look at the cylinder picture again, here is a phi RC, phi SC. On the cylinder, okay, without this, we had, oh, I should have said this. This is important. Okay, that if you calculate B0 minus with G, B0 minus is integral Z B0, sorry, Z BZ dz minus integral Z bar B bar Z bar dz bar. So you are calculating commutator between this and integral dz prime over z prime chi of z prime. So this commutator will get contribution whenever this OP has a singularity. Okay, this has no singularity because this is holomorphic, the anti-holomorphic. So this we can forget. Okay. So let's recall that chi has a term C del xi plus other terms. Okay. This is the only term that has a singularity with B. Okay, because BCOP gives to 1 over z minus z prime. Okay. So this integral will give you integral after you pick the residue. So this z will cancel the z prime because z will become z prime. Okay. So this will give you integral d z prime del xi z prime, and that is 0. Okay. If you had used any other function, instead of dz prime over z prime, instead of averaging like this, you could have say averaged over something else. Okay. dz prime times z prime to the n. Okay, and then divide by appropriate normalization. Okay. That wouldn't do because you see that will give an extra z prime to the n, and that will not give you 0. So we need to average in this fashion, okay, the uniform average in the w coordinate to get a 0 answer. Okay, so what this is saying is that this cylinder, okay, with this, the contribution is here 1 over L0 plus L0 bar, delta L0 plus L0 bar, delta L0 plus L0 bar should be 0. Okay. And then you have the B0 B0 bar. Okay. But there is also a G. Okay, that's the net operator that is inserted between phi RC and phi SC. Okay. Now, recall that this object is 1 over k square plus m square. Right? And this we had interpreted as a standard propagator. B0 B0 bar are just some momentum independent objects, right? So they don't keep producing a momentum factors. But now you see you have a G. Okay? G contains chi, which has matter fields, right? Because it has a gamma TF contribution, right? Chi, the next term here is gamma TF, okay, which has matter fields. So G can produce momentum dependent contribution, right? The matrix element of G between phi RC and phi SC could have momentum dependent contribution. Okay. So now you have a propagator, right, which has the standard denominator k square plus m square, but also has a numerator which can be momentum dependent. Okay, and in fact, typically it's linear in momentum because the TF has a psi del x, right? Psi dot del x, and del x acting with e to the I k dot x will pick up a factor of k.
Sorry, could you repeat why G has momentum dependence?
G doesn't have momentum dependence, but G has matter fields, right? Gamma TF is part of
Yeah.
gamma TF. I think chi has e to the phi TF, right? Q had gamma TF, chi has e to the phi TF. Right? Where TF is the matter super stress tensor, and that has psi dot del x.
Yes. Okay.
So this del x, when you take, suppose there is a momentum carrying state here.
Yeah.
So this del x
Ramond,
will bring down a
you
factor
want
of k.
Ramond sector right now.
Exactly. We're in the Ramond sector. So there will be terms linear in k in the numerator, right? So G will be k dependent term. And we see that indeed that this has the correct interpretation as a propagator, because for fermions, we are in a Ramond sector. So what is propagating in this along the cylinder is the fermionic state. Okay? And the fermionic state, as you know, does have numerator factors which are momentum dependent. Okay? And it's precisely those numerator factors that come from this extra PCO insertion that you have, right, in the form of G.
Also, it's delta L0 comma L0 bar, right? That Kronecker delta.
Yeah. Or delta L0 plus, sorry, L0, yeah, right. So this should be minus. Yeah, you can write it as this or delta L0, L0 bar. Okay. Other questions?
I mean, where exactly are we like putting this PCO circle?
Anywhere,
Anywhere
doesn't
on the
matter.
plane.
Because once you have put it on a circle, right?
Okay.
Then the B zeros commute with G.
Okay.
And
And
L0 is also,
L0 anywhere is commuted.
yeah.
Okay.
So now, I mean, here in the, once you have written it this way, it doesn't matter where you place what, because everything commutes with everything else.
Okay.
Right? G commutes with B0, B0 bar, L0 plus L0 bar. These commute with L0 plus L0 bar. So you can put them anywhere. Any other question? Okay, so this is as much as I'll say about the choice of PCOs, right? As I said, if you want to go beyond this, right, to actually apply it, right, this particular procedure for solving problems with divergences, right, for spatial momentum, like mass renormalization or the vacuum shift, right, flat poles or mass renormalization, there you really need string field theory, right, to go beyond this. So to go beyond this, we need string field theory, which we are not going to discuss. Okay, but this choice of PCO, the distribution of PCO is the primary constant that you have to remember. There is one other thing maybe I should say, that the same analysis holds for non-separating type degeneration. Okay, like I think I get it right correctly. It's like that when these are sigma, right? When the neck of sigma pinches, right? So the only difference is that here the two punctures that are generated by this neck, pinching, okay, are on the same surface instead of being on different surface. Okay? But again here for NS we do not need any insertion. For R we need G insertion. Okay, I mean, there's identical analysis that one can do in this case as well. And which is just as well because the propagator shouldn't depend on whether it's connecting two different Feynman diagrams or two parts of the same Feynman diagram.
Could you tell what is the factorization level statement here? It should just come out as a 1 over k square plus m square plus into the rest of the diagram.
Yes, that's right.
Okay.
1 over k square by m square also is this B0 bar.
Yeah.
Right? Times the rest of the diagram. Right? So it's basically this. It's this propagator. Right? For NS sector, it's this quantity. And for Ramon sector, for our Ramon sector is this quantity. For NS sector, there is no G. Right? So you put this between phi RC and phi S, and then multiply by the first diagram and the second diagram. That's a that's a factorization statement. I can write it also there. So basically the contribution from near Q equal to 0 will be sigma 1 amplitude with extra phi S times sigma 2 amplitude phi R times phi RC B0 bar. So this is for R. In NS, you don't have this. In NS, it is absent. And so that's the factorization statement, and this is exactly what happens in a normal quantum field theory. Okay, so next, I think I have, let's see, I have 15 minutes. I think I'll just discuss one more topic today, okay? And that is supersymmetry. The question is, how do you see that the amplitudes are supersymmetric? Okay, now there are the supersymmetric word identity. So basically, it means that in an amplitude, you have to vary each external state one at a time, and the sum of the variations should give you 0. So this for normal symmetry, normal word, say normal derivation of word identity. The way it goes is that typically we have a dimension 1 current could be holomorphic or anti-holomorphic, let's say J of Z or J bar of Z bar, something like this. And then we use suppose you have a Riemann surface with many insertions. We start with the fact that if you take a contour like this, integral J of Z dz is 0. Right? Because there is no pole, this is holomorphic, and then there's a pole in the interior. Okay? And then you deform the contour outwards. Okay? So then deform it. Picking residues at vertex operator. Okay? And again, you may worry about what happens at the handles and so on. But as we had discussed once, as long as J is periodic, has correct periodicity, we only get vertex contribution. Okay, the handle doesn't really make a difference. Okay, the existence of the handles, you can just wrap around the handle and move it around one cycle and make it cancel the earlier contribution. Is this clear? So this gives an identity, right? So you start from 0 and this you express as a sum of terms. With integral Jz dz applied to each vertex operator. So the idea is that if we can find something similar to Jz for supersymmetry, right? Imagine that we had found a current that corresponds to that generated space-time supersymmetric transforms of the vertex operator. Namely, that when you do a contour integral of the current around the vertex operator, it will tell us how the vertex operator changes when you apply the space-time supersymmetric transformation. Then we could apply the same logic. Okay? Start with integral Jz dz equal to 0, then deform the contour, pick up contribution from each vertex operator, and that's the way you'll get the supersymmetric one identity. Okay? So the question is, what is Jz for supersymmetry? Okay, Jz or J bar Z bar.
Here we don't worry about PCOs.
Yeah, you have to make sure that it can be passed through PCOs. Indeed, that's needed.
That this current commutes with PCOs.
Exactly.
We are talking about target space supersymmetry here, right?
Yes, target space supersymmetry indeed.
But that won't be. I mean, that will be of different nature compared to the worldsheet supersymmetry we have, right? Like for like,
Yes, indeed. They're completely independent, right?
or I mean, is it clear a priori that it will even have a current corresponding to it?
Yeah, if it does have a current, then we
Some
can
0,
prove.
1.
Yeah,
Or
if
1,
it
2.
does have a current, then we can prove the supersymmetry of the results, right?
Okay.
It's like if you have a translation invariance, right? Suppose you want to prove that the amplitudes are translation invariant, okay, on a generally Riemann surface. That's also a target space symmetry, right?
Yeah.
More observation.
Oh, right. Del X, like if
Yeah.
I
There you
draw
choose for
Del.
Jz as del x.
Okay.
Okay. So the question is there an analog of del x for supersymmetry?
Okay.
So it turns out that the choice, the supersymmetric current, has the form J. A is just an extra level with the spinor level. Which is e to the minus phi by 2 SA. Okay, let me just call this sigma I just to give it a name. We'll call it sigma A. And sigma tilde A, which is e to the minus phi bar by 2 S bar A for 2B and e to the minus phi bar by 2 S bar A dot for 2A. I don't remember if I call them S bar or S tilde, whatever it is, these are the anti-holomorphic version of the spin fields. Right? These are the spin fields that we had introduced earlier. This as well as this. Okay. So sigma indeed can be shown to have dimension 1, 0 or 0, 1 has dimension 0, 1. Sigma bar A or A dot has dimension 1, 0. Okay. So it does make sense to write a word identity involving sigma A dz and sigma bar A or A dot dz bar. Is this clear? Okay. And one can also check that these have no singularity with the PCO insertions, because PCOs involve something like e to the phi. The C del xi, of course, has no OPs. So the only dangerous part is the e to the phi TF. So TF has psi del x. So e to the phi with e to the minus phi by 2 has z minus w to the half, and psi with s has z minus w to the minus half. So this has a non-singular OP with the PCO insertions.
Okay,
Okay,
what is this notation? Sigma bar A comma A dot?
Oh, A is for 2B and A dot is for 2A.
Oh, either.
Yeah. 2B, this is for 2A. Okay, is this clear? Are there questions? So the only subtle point here is the periodicity. That turns out that sigma A and sigma tilde A or A dot are periodic on the Riemann surface after summing over spin structure. And that's not very hard to understand. So, okay, we can even just do it for the torus, right? Imagine that you have a sigma, okay, inserted here. So as you know that the sigma A creates a branch cut for psi mu. So this produces branch cut for psi mu. So now imagine what let's suppose to begin with, psi mu was periodic. Suppose psi mu had periodic. Then if you take this sigma A, okay, and then go once around the loop, around the A cycle. So you see, during this process, you will cut this contour once, right? So as a result, what is going to happen is that the sign of psi will jump, okay, will change as it crosses the path of sigma. Okay, because there is a branch cut. Starting from sigma, there is a branch cut for psi mu. Okay. So if you take sigma and come back to the original part in that process, okay, you will change the periodic boundary condition to, so after moving sigma, so here is it. So after moving sigma A along, say, A cycle, the psi mu BC boundary condition along B cycle changes. Okay, so if it was periodic, it will become anti-periodic, and vice versa. Is this clear? And changing the boundary condition of psi mu is the spin structure, right? That means the spin structure changes. Okay. So if we take sigma A and move it once around the A cycle, what it will give, it will not be periodic. What it will produce is the amplitude in a different spin structure, because where psi mu has now picked up an extra minus sign. Okay. But after you sum over spin structure, okay, then the sigma A amplitude becomes periodic. Okay. So this is important to remember. So the supersymmetry, so space-time supersymmetry can be seen only after summing over spin structure. Okay, so I think today I'll stop here. Are there questions?
Can you explain this once more? This why sigma A move along? What does it even mean to move sigma A along? Yeah, this
Yeah.
time.
So I'm trying to see if suppose sigma A has an argument z, right? And I'm trying to see if the correlation function of the sigma is, there are other operators here, right?
Okay.
I'm trying to see if the correlation function of the sigma is periodic along the A cycle.
Okay.
Okay. So I take the argument of sigma and move it continuously, go around the A cycle and come back to the original point.
Yes.
Okay. I want to know if the correlation function is invariant under this. We'll come back to the original value, right?
Right. Right.
And what I'm saying is that what will happen is the correlation function on a given spin structure surface will not come back to the original value, but it will come back to the new correlation function, which is the correlation function in a defined spin structure.
Okay.
Because psi mu had periodic boundary condition along the B cycle. Now that will turn into anti-periodic boundary condition along the B cycle.
Okay.
Okay, because of this branch cut. So it's as if you are that. So it's happening that, imagine that the sigma A, starting from sigma, there is a branch cut. Okay. So what we are doing is that we are taking the torus. So imagine that there is a sigma and there is a branch cut. Okay. And the branch cut may end on some other vertex operator. Okay. So earlier, what would have happened is that if psi was moving along a cycle avoiding the branch cut, it would have been periodic. If it crosses the branch cut, then it will be anti-periodic, right? Because there is an extra minus sign that picks up while crossing the branch cut. Okay. But now if you take the argument of sigma and go once round, okay, you have drawn the branch cut all the way around the torus, around the A cycle. Okay. So now the A cycle has that extra branch cut, the whole of A cycle, right? Because you have taken sigma and gone around the whole of A cycle. Because the branch cut extends as you are moving sigma. Okay. So now the boundary condition along the B cycle would have changed because B cycle intersects A cycle, right? So as it crosses the A cycle, there will be an extra minus sign. Okay. So this is the reason why, if to begin with, the boundary condition on psi mu was periodic along the A cycle, along the B cycle, after you have moved sigma along the A cycle, it will become anti-periodic and vice versa. But after summing over spin structure, of course, it should be periodic.
Okay. Okay.
Okay. So it's basically saying that if you have a amplitude with in various spin structure section, right? A and B cycle, A plus plus, A plus minus, plus A minus plus, plus A minus minus. Okay. Then one movement of sigma permutes this. Okay. So A plus plus by itself doesn't remain invariant, but the whole sum remains invariant. So that's the statement. This is periodic. Are there other questions?
How did you get this current actually, Susi current?
How did you get this? Well, this is dimension. You can check that it's dimension 1 current. Let me. Yeah, so this is dimension 1. Dimension 0, 1.
Yeah.
So it does something, right? It's conserved. So
Yeah.
generate some odd identity.
Yeah.
And it converts, you can see it from minus, if you start with a minus half picture vertex operator, which is a fermion, it will convert it to a boson, right?
Yeah.
And vice versa. If you start with minus 1 picture vertex operator, it will produce a minus 3 half picture fermion.
Yeah.
So it does convert bosons to fermions and fermions to bosons.
Yeah.
Right? And it is conserved. So whatever work it generates is what we declare as supersymmetry of the theory.
But is there a way to derive these things by Noether procedure or something like you do for Lorentz generators and so on?
For Lorentz generators, you know how? By Noether, you are saying.
Yeah.
Yeah. See, the point is here, the worldsheet didn't know about space-time supersymmetry, right? The space-time supersymmetry came after you have summed over, we did the GSO projection and summed over spin structure.
Yeah. Yeah.
So that's why it cannot be constructed as an Noether current from a worldsheet perspective. Right? Not in RNS. There are other versions like pure spinor or Greenswartz where you can get it from a Noether current, where the worldsheet theory itself has manifest supersymmetry. But in the RNS, the worldsheet theory doesn't have manifest supersymmetry.
Okay.
But the very existence of a current, of the conserved current like this, right, and the fact that this is periodic, means that there is some order identity that it generates.
Yeah, sure.
And you declare that as a supersymmetric order identity.
Yeah, okay.
And if you recall, this also appears in the gravitational vortex operator, right? So that's another indication that this has something to do with supersymmetry.
Yeah, sure.
Okay. Any other question? Okay. If not, I'll stop here. And next week there will be a regular class.